We're now ready to talk about anhydrides. Anhydrides is the next reactive compared to acid chloride in terms of nucleophilic attack to the carbonyl group. We're going to first, again, learn how to name them, and then we're going to look at the reactivity of anhydrides in terms of varying the nucleophiles and seeing what kind of products we get. So for nomenclature, it once again is very easy. You replace the acid part with anhydride, right? So if you're naming symmetrical anhydride, in other words, you have the same R group on both sides. So let's just do with a specific example. You look at the if this wasn't there and it was OH there, how would you name that acid? It's, you know, if you're following the IUPAC name, you would call that ethanoic acid. So you might call that ethanoic anhydride, or you would use a common name more often for the two carbons. This is acetic acid, the vinegar, so then this is called acetic anhydride, which is very common reagent, acetic anhydride. All right. Now, if you have unsymmetrical, so here's an example of symmetrical, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what would the name of this be? 5 carbon, including the acetyl would be, if this wasn't there and it was an H, it would be 1, 2, 3, 4 pentanoic acid, right? So it would be pentanoic anhydride. All right, but we have a problem here in which the R groups are not same, but it is still an anhydride. So then what you do is you name both acids. So pretend that this part is the acid, so that would be 1, 2, 3. You have a propanoic, and then pretend the H is on here, then 1, 2, 3, 4, 5. That would be pentanoic, right? And what you do is you say both acids, pentanoic, propanoic, put it in alphabetical order, followed by anhydride. All right. So more complicated cases, just pretend it's an acid, because you have no problem naming acids. Even if you have like students get stumped if you have like, you know, substituents coming off of it and things like that. Just pretend there's an H here, name that acid, and then flip it over, pretend there's an acid here, name that. Put them in alphabetical order, followed by anhydride. All right. Given a name, you should also be able to draw anhydride, which students do have problems with because they don't have the anhydride functional group totally memorized when they do that. So remember, oxygen is in the middle, and then you have 2 carbonyls flanking it, and then part of the name, that carbon is part of that. So if it's like propanoic, that's 1, 2, 3. The 3 carbons are included in with the carbonyl. All right. So that's the nomenclature, and we're going to now talk about the reactions. And I am not going to go over like in detail like I did with thionyl chloride, because the reactions are exactly the same. All right. So let's look at how you will make anhydrides initially, which should be reviewed for you, and then we'll go over all these reactions very briefly. All right. So you could take 2 equivalents of acid and heat it in high heat, but that only works for acetic anhydride. So this is really not a practical method. So this, however, is the way that most people would make anhydrides, which is that first you get rid of this proton with the base. So you form a nucleophile, an in this case, an acetate, sodium acetate, right? But any carboxylic acid, if you remove that proton, it becomes a lot more nucleophilic, right? Then you react it with some kind of acid chloride, because you know that acid chlorides are very reactive. So if, for example, you want to react with this chloride, then this is the nucleophilic center that's going to go and attack, form the tetrahedral intermediate, come down and make the chloride leave, and then you have the anhydride. So in this example, you have O, and then, so that will be acidic and then benzoic anhydride that you'll be making in this example. All right. So that's what I highly recommend in a synthesis problem, that you use this method and forget about this heating method. All right. So once you have anhydride, you're going to do various nucleophilic reactions, as you see here, one of which is hydrolysis. All right. So look at the chemistry that we did for acid chloride. You could go back and review. Okay. So you know, if you know the acid chloride chemistry, this was the leaving group in which the nucleophile replaced it, right? The only difference in anhydride is that the leaving group is just a little bit bigger. So this is the leaving group when a nucleophile comes and attacks the carbonyl. Okay, so for example, the acetic anhydride with water, you know, imagine in your head that the water is the nucleophile coming in and attacking this, making O minus comes down, and then now this whole thing is my leaving group. All right. So when you react with an alcohol, notice the OR replaces this. In amine, the NH2 or NR, depending on whether it's unsubstituted or substituted. So that's all same chemistry. And then same chemistry with lithium aluminum hydride and lithium alkoxyhydride, Grignard and cuprates. Okay, so if you take a look at side by side, let me just zoom it down so you see the similarity. You see that everything is exactly the same, the products. Okay, the starting material is different, but it does the same exact chemistry. Right? So hopefully, when you do these problems, it's going to be a review for you in terms of sort of redoing the acid chloride chemistry, except that the leaving group is much bigger. Right? Probably the only the challenging part would be if you had an unsymmetrical anhydride. So let's say we have a CH3, C-double-O, O, C-double-O, and then you have something like this, let's say, right? Unsymmetrical anhydride. So if I have the nucleophile, where do you think that the nucleophile will be more attracted to? This carbon right here or this carbon? Because now we have two carbonyl that are not exactly the same. So in this example, it should be very easy to for you to predict where the nucleophile is going to attack, right? Because in this case, the alpha carbon has 3 chlorines on it. So these are all electron withdrawing, so therefore is pulling electron density towards itself, causing this carbon to be even more electropositive. So don't you think the nucleophile is going to be more attracted to this carbonyl of the anhydride than the other? So that would be the prediction. And then what would happen is this would come down, and remember this is the leaving group, right? So then we would have that as the product, and the byproduct will be an acetate. All right. So you have to kind of, if you're given an unsymmetrical anhydride, ask yourself what is different about the two carbonyls. It could be electronic, like it's as in this example, or maybe it will be steric, like maybe it will have a huge T-butyl group on it, preventing this carbonyl to be accessible, to be attacked nucleophilically. So in that case, it'll attack here and then make this leave, for example. So you have to use your common sense in unsymmetrical anhydride in trying to predict what would happen. All right. And also, the students a lot of times have problems with cyclical anhydride as shown here. That's why I've put this in your drill. Don't overthink this. Just, I mean, if it helps you to make a model of this and then try to figure out what's going on, then that's fine. But like, just think of the cyclic molecules as a circle, okay? And then when something comes and attacks at the carbonyl, it's a symmetrical, so it doesn't matter. And then it forms this intermediate. It's going to do the same chemistry, right? O minus is going to come down, and then it's going to kick out. This is the leaving group, correct? So then you're going to have something in which it opens up the ring that the anhydride was part of, because what you're doing is you're basically, pretend I have a scissor and I'm cutting it when I do this, when the leaving group leaves, right? So in this problem, I have two rings stuck together. So if I have a ring here and then another ring here, and this is where the clipping occurs, notice this string is still intact and this string is still intact, which is what you're seeing here, all right? So just because anhydrides in a cyclic form, do not get overwhelmed. Just do the same chemistry like here. See if you could do these problems before class, as well as 21.12a, which is just a naming, and then 21.21. All right, so that concludes the anhydride chemistry.